I want to do an epsilon delta proof from beginning to end, but again, illustrate what is the point of the process. Here I have a picture, y equal f of x, and it appears f of a is equal to L. Now, the nice thing is it doesn't matter if f of a exists or not exists. The limit is independent of the functional value. So the concept, I want to prove this statement right here. What we do is we do a neighborhood around L, and we call it an epsilon neighborhood. So that would be L plus epsilon, and that would be L minus epsilon. And the idea is really simple. If I go out to the curve and I project it down, I want to know there's a value delta that will always put me within that projection. So this would be a minus delta, this would be a plus delta. Now, what makes this difficult is the more I squeeze here, the more I'm going to squeeze here. So I have to have a delta that moves with epsilon. Delta is going to have to be a function of epsilon to guarantee that no matter how much I squeeze this, I squeeze this. That is how we prove that L is in fact the limit. If I had chosen a value that was different than L, maybe above or below, and I projected out, I would miss A absolutely 100% of the time. So the proof, the physical proof actually looks like this. Whenever 0 is less than the absolute value of x minus a, and that's less than delta, this is a strict inequality, which means x is never going to equal a. It's just going to get really, 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 really close. This would imply that f of x minus L is less than epsilon. So this is my goal, is to write a proof where this is the first statement of the proof, this is the last statement of the proof, and in between I'm going to do the algebra. So there's a two-part process. A lot of people think we're just repeating our steps. What we're actually doing in the first part is figuring out the exact value of delta to choose so that I can write this seamlessly. And that's why the algebra does appear to reverse itself. So let's do a very specific example of this. Okay, so let's suppose the function in question that we're looking at. Let's suppose that f of x is equal to 2x minus 1 when x is not equal to 3, and it equals 8 when x equals 3. So this is sort of an interesting graph. It's a line that would be the point 3, 5, and that would be the point 3, 8. So do a quick check here. It looks like the line y equals 2x minus 1 for all values except 3, which means I've removed 1 point from the graph, and then I filled it in somewhere else. So the functional value, f of 3, in fact, equals 8, but what we're doing is we want to prove that the limit as x approaches 3 of f of x is in fact 5. The strange thing is there is never going to be a y value of 5. We just want to prove that the limit is 5. So as we start the process, our first half of the proof is to figure out the value of delta. Then when we physically write the proof, like we said, we kind of reverse all of our steps. So the proof starts like this. For every or for all epsilon greater than 0, the absolute value of f of x, that guy right there, minus the limit is less than epsilon. That statement then implies the statement that 2x minus 6 is less than epsilon. Now, I can easily factor a positive 2 out of the absolute value. So that would imply that 2 times x minus 3 is less than epsilon. And I can simply multiply both sides of an inequality by the same positive value to preserve the inequality. So that would imply that x minus 3 is less than 1/2 of epsilon. Now I have it exactly in the form I need. You see, x is approaching a, x minus a needs to be less than delta. So clearly our choice of delta is going to be 1/2 epsilon. So now we say choose, and that's an important term here, choose delta to equal 1/2 epsilon. Okay, that's our scratch work. That's our algebra. We haven't actually started the physical proof yet. Now we will write the proof because we know exactly what value to use for epsilon. So now the proof starts with the statement, whenever x minus 3 is less than delta, and notice again the strict inequality because I'm never going to equal 3. In fact, in this case, there's a hole there. This would imply that x minus 3 is less than 1/2 epsilon. Now I'm essentially going to do this proof, or excuse me, this algebra in reverse, because we already know what the algebra is going to look like. So now if I multiply both sides by 2, now if I distribute the 2 into the absolute value, which I can because 2 is positive, and then finally, I restate that as 2x minus 1 minus 5 is less than epsilon. This is the form of an epsilon delta proof for a linear function. It turns out if I was dealing with something more complicated and nonlinear, most of the steps remain the same. And again, our main goal is to find the value of delta that makes this proof. Okay.